So today we'll start discussion on can there be spinorial conserved charges. We know commuting conserved charges, electric charge, monopole charge, SU2 non-abelian charges. They are all commuting in the sense that they are of Lorentz, they are spin zero representations of Lorentz group. Can we have conserved charges or P mu generator of translations? These are spin 1 vectorial conserved charges. Can we have spin half, spin 3 half, and those would be spinorial charges? Can we have conserved spinorial conserved charges? So which means can there be conserved charges with spin 1 half or 3 half or 5 half, spin 0 or spin 1 we know. So now let's try to see if there are, what kind of a algebra must they satisfy. So let's start with possible n spin half charges. Now these can come in two categories. Let me call them Q alpha I, where I is 1, 2, 3, there are n of them, and alpha is the spinorial index. And these are half zero representation of Lorentz group, left-handed spinorial charges with spin half. And there could be correspondingly right-handed spinorial charges with spin half, and that will correspond to Lorentz group representation 0 half. Now if such charges are conserved charges, then their anti-commutator must also be a conserved charge. So what is the anti-commutator? Spinorial, therefore we will be talking about anti-commutators. Also has to be conserved. Has to be a conserved charge. Now if it's a conserved charge, what kind of a representation of Lorentz group it can be? These objects are half zero times 0 half. Product of these two charges under Lorentz transformations transforms like half zero times 0 half. And this product, if we break it into reducible representations, we know how to compose spin halves. Spin 0 and spin half gives me half, and spin 0 and spin half gives me spin half. So such a charge, which is the commutator of this object, which has to be conserved, has to be in Lorentz representation half-half. Now do we know any conserved charge which is in the Lorentz group representation half-half? There is one, the energy momentum vector. P mu. You can write P mu in a matrix form, P0 plus P3, P1 minus IP2, P1 plus IP2, P0 minus P3. The four components of P mu you can break into the matrix form, the zeroth component plus third component, first component minus I times second component, complex conjugate of that, and zero component minus P3. Now this object is simply sigma mu that we had defined of alpha dot times P mu. Remember what was sigma mu that we had? Was a unit matrix and three polymatrices without I, right? Let me check. Yes, without I. So if you put that in here, that's exactly this matrix. And sigma mu alpha dot under Lorentz transformation alpha transforms like spin half, and alpha dot half precisely transforms as half. So clearly if such a conserved charge exists in nature, then the commutator of these two charges will be proportional to P mu. Q alpha I Q bar alpha dot J commutator has to be proportional to sigma mu alpha dot times P mu. Now if I interchange I and J in this commutator, it is symmetrical. So therefore it could be delta Ij. Sorry, one of them is alpha and other one is alpha dot. And then for some convenience we put a numerical factor 2. That's a convenient normalization. So if at all there are spin half charges Q alpha and Q alpha dot, and if they are n in number, then their anti-commutator should be proportional to P mu through this object. Next, now can there be spin 3 half conserved charge? Now this we realize that spin half conserved charge can be there, but then it must have the property that its commutator of these two objects should be proportional to P mu, anti-commutator of these two objects. But similarly we can ask the question, can there be a spin 3 half conserved charge? Now spin 3 half conserved charge, let me call it Q mu. alpha I and q mu bar alpha I j, and evaluate this anti-commutator. Now this object is spin 3/2 in the Lorentz representation, 3/2 0. This one is 0 3/2. Notice the dimension of spin 3/2 0 representation is, dimension is twice spin plus 1, 2j plus 1, that is 4. Similarly, this one also 4. But the way we have written it here for each one of them, for each I, right? We have written 4 labels here and 2 labels here, it's 8. There are 8 complex numbers here. But this is supposed to have a dimension only of, should have only 4 independent complex numbers. So if I construct spin 3/2 objects from these objects, they must be subject to some constraint, and exactly 4 constraints. So that out of the 8 complex number, only 4 of them are independent. So you think of that these objects are subject to those 4 constraints, and 4 constraints essentially are gamma mu times q mu equal to 0. But let's not worry about that detail. So you have constructed them with constraints, they satisfy certain constraints, but then their commutator again has to be a conserved charge. Anti-commutator has to be again a conserved charge. But under Lorentz group, how would it transform? The same argument, under Lorentz group, this is a product representation of 3/2 0 times 0 3/2. So under Lorentz group, it will transform as 3/2 3/2. Because 3/2 times 0, spin 0, which means 4-dimensional spin 3/2 representation times spin 1-dimensional spin 0 representation gives you a spin 3/2 representation only, because this is a identity representation, and this times this is 3/2. I mean, the general rule of SU2 representations, spin j times j prime, if you remember, is representation j minus j mod prime spin plus j minus j prime mod plus 1 representation plus spin j minus j prime mod plus 2 up to spin j prime plus j prime. This is the composition rule for multiplying 2 spin representations and then reducing them in terms of irreducible representations. So that's what we are applying here. But now the question is, again like we asked here, is there any conserved charge which lies in the Lorentz representation 3/2 3/2? There is a theorem due to Coleman and Mandula. Now, this is spin 3/2. This is not a spinorial representation. It's more like this object, which was p nu, vectorial representation. So it is a bosonic charge. So this is a bosonic conserved charge, and Coleman-Mandula theorem tells us that there are no bosonic conserved charges other than spin 0 and spin 1. So, in an interacting theory, so therefore there cannot be, so this is not available to us, therefore these cannot be conserved charges. So only possible, and similarly if you go for 5 half, 7 half, the same argument is valid, because you will want spinorial charge, you would need tensorial or vectorial tensorial conserved charges of higher spins, and there are none. So the only possible spinorial conserved charges are q alpha I and q bar alpha dot I. It would be a tensor.
So something like T mu.
Yes. Very good.
So why?
Very good. Very good. Very good. Very good. That. Very good. T mu nu or M mu nu, right? M mu nu. Lorentz generator itself, right? There are 6 of them. What representations are they of Lorentz group themselves? If they form a composite representation. Self-dual pot is left-handed. If you remember, for fermions we found that generators were sigma mu nu, right? Let me do it aside here. Sigma mu nu, right? Which broke into small sigmas in the diagonal form this. This is the self-dual pot. This is the anti-self-dual pot. This object lives in half, here 1 0 representation, this object lives in 0 1 representation. And that counts the numbers, independent numbers also. Total number is 6. This dimensional is this object is 3-dimensional, this object is 3-dimensional. So they come under the Coleman-Mandula theorem. But anything more than that is not there, right? So we said only possible ones are these ones, but then we already worked out what is the algebra of 2 q's, q and q bar. But then we must also have algebra of what is q with q and q bar with q. So q alpha I anti-commutator with q beta j, what is this object? Now in terms of Lorentz rotation properties, it is 0 half, half 0 times half 0. Half times half is 0, and half times half also has 1. By the rule we wrote there. So now this object can be broken into this anti-commutator into a conserved charge which has to transform like this, and another conserved charge which has to transform like this. Similarly, q bar alpha dot I, q bar beta dot j, which is 0 half times 0 half, will have to transform as 0 1. Like I already said, is that this object, possible conserved charge, we could write it as sigma mu nu times m mu nu alpha beta. See here, sigma mu nu would pick up the self-dual part because sigma mu nu is self-dual. So therefore, this object could be this one. Similarly, this object here could be sigma mu nu bar m mu nu times alpha dot beta dot component. So this commutator could have one piece like this. We have not analyzed this piece, we are analyzing this piece. Could have one piece like this. But then an algebra of conserved charges has to have their relations, commutator relations or anti-commutator relations. Besides that, they must also satisfy Jacobi identity. So then if you check Jacobi identity, then you realize is not allowed, because you can just put this in with an arbitrary coefficient alpha here and take the three of them. Jacobi identity is property of three generators. Take the anti-commutators in different sequence, cyclic sequences, and work them out. And in order Jacobi identity to be valid, you will find out straightforward algebra, the alpha has to be 0. So which means Jacobi identity does not allow this charge to be in this anti-commutator. Similarly, this charge. So that leaves us the possibility of only these Lorentz group trivial representation. Spin 0 charges. So I write q alpha I, q beta j anti-commutator is to be Lorentz group invariant object, because this product can have, if these have conserved charges, this representation can be only in this object, which means Lorentz invariant representation. And we did an exercise last time. What is a Lorentz invariant object with two indices alpha and beta? It has to be proportional to alpha, epsilon alpha beta, because that's the only Lorentz invariant object we have with spinorial indices, which transforms, which is unchanged by Lorentz transformation. So it has to be proportional to this. But this object is antisymmetric in alpha and beta. This anti-commutator is symmetric in alpha and beta and I and j. If I interchange alpha and beta and I and j together, change alpha and beta and I and j, then it's a symmetric object. Then it has to be some charge Zij, which is a Lorentz scalar, because this object is a Lorentz scalar, and has to be antisymmetric. And then, because this is antisymmetric in alpha beta interchange, this is antisymmetric in I and j interchange, this object is symmetric when I interchange this pair alpha I with beta j. Clear? And then, for some convenience, we put certain normalization, 2 times root 2. Now similarly, I can do for q bar alpha I, alpha dot I, q bar beta dot j, and that would be 2 times root 2 epsilon alpha dot beta dot Zij bar, some another Zij, and call it Zij bar, with the same property that Zij bar is minus of Zji bar, antisymmetric in Ij indices. So Zij and Z bar Ij are spin 0 conserved charges. So if nature has spin half conserved charges and n of them, I goes 1, 2, 3, 4, n, then their algebra is, why did I write it? Somewhere I wrote it? Yes, here. That q bar anticommutator is proportional to p mu, and q anticommutator is proportional to z, and q bar to z bar. What z bar and z are some spin 0 conserved charges, these are new conserved charges. So such a theory, in addition to having spinorial spin half charges, would have spin 0 charges, new charges. Now notice, and there is a name given to these charges. These are called, what is called? Central charges. And this, since they are spin 0s, they commute with all others. So before I did Z and Z bar Ij commute with Q alpha I and Q alpha bar dot j. So then this relation 1, this relation, these two relations with these properties for them, and this property completely defines a closed algebra. And they satisfy Jacobi identity. But we'll do. Now notice if there is only one q charge and q bar alpha charge, which means n is equal to 1, that I called, I think, capital N, right? If n is equal to 1, which means there is only one pair of spinorial charges, q alpha, transform left-handed charge, and one right-handed charge, then central charge is 0, because with n equal to 1 I cannot have a central charge here, because I is equal to j, both are 1 1, but this has to be antisymmetric. So then q alpha anti-commutator q beta is 0, q alpha bar dot q beta dot bar is 0. But if n is equal to 2, n2 or greater than 2, we have central charges. And for n equal to 2, we have one pair of central charges. Z12, call it Z, and Z bar 12, call it Z bar. One complex spin 0 central charge. Now, in order to give the representation completely, we have given this relation here, we have given these relations here, and we have also stated that Z commutes with all of them. But what about this generator, P mu? Because that's also a conserved charge. How does P mu and what is the P mu and Q algebra? So which means P mu Q alpha I, a commutator. Now this is a bosonic charge, this is a fermionic charge. So the corresponding relation is commutator. What is this and what is this? So let's start with this, P mu Q alpha I. Now under Lorentz transformation, P mu is half representation, and Q alpha is half zero representation. Now use the same logic and break this product of two representations into irreducible representations. Half and half can give you 0, and half can give you 1. So the first entry is 0 and first entry is 1. And half and 0 gives you half, half and 0 gives you half. Similarly, is 0, 1, half, half. Now this is a spinorial charge, this is also a spinorial charge because it has spin half integer, spin plus this plus spin plus this, that's half. But then we learned that we cannot have hard spin representations from Coleman-Mandula. So Coleman-Mandula theorem kills this. So the only possibility for these commutators is a spin half charge, conserved charge, and spin half conserved charge. But spin half conserved charge we already know. So it has to be so P mu Q alpha I commutator has to be proportional to, this is right-handed. See, this was left-handed, this is right-handed. So it has to be proportional to Q bar alpha I, alpha dot. Times some object which is indexed mu and has spinorial indices alpha alpha dot, so that you have the alpha here, alpha dot are summed. What C mu is some arbitrary object. Similarly, you do it for this one. That will be proportional to Q not barred. P mu Q alpha dot bar I would be C mu, some C mu bar or whatever we call it, alpha dot alpha Q alpha I. You cannot have Q bars and Q because it has to be Q bar only.
No, say in the case of Q bar, first one, can we not have a linear sum of the Q bar? Say Mij times Q bar alpha dot j.
In this one, is this the relation that you are asking for?
Sir, let us take the case of the first.
This first one.
Yes, just that.
Now the first one has to be from the properties of Lorentz group representation only spin half 0.
Saying that I index also can receive the other
Yeah, you could do that complication. I mean I index. Maybe you could put here ij also. Yeah, you could do that also. You could do that. Make it more complicated. Do it. Because it doesn't matter if whatever complicated you make, you go and check then Jacobi identity. And if you check Jacobi identity, you realize so that means P mu Q alpha I commutator is 0, P mu Q bar alpha dot commutator is 0. This is the additional set of relations of this algebra. Now what about what about the relationship of Lorentz generators mu nu, because they are also conserved, right, with these charges. Lorentz generators. Now let me write it again. If mu nu q alpha I, Lorentz transformation properties of this object are, this object, like we said earlier, is made up of self-dual part and anti-self-dual part. Self-dual part transforms as 1 0 under Lorentz group, and anti-self-dual part 0 1. These are three independent complex numbers, these are three independent complex numbers, and that's what M has, times half 0. Now this object is 3 by 2 0, 3 by 2 0 plus plus 1 half 0 plus half 1 plus now this times this is 0 3 half. Did I do everything right? Something is not right. Something is not right. This times this is half this, right? Half 0 0. This times this is half and 1, that's correct, and this times this is half and 1. Is it now right? Huh? Yes, there are two of them, right? One comes, no, this is this. Oh, there's only one, that's what you're saying. There's one. This times this and this times this. That's it. All right. So that's it. So we have these representations. Now this is not allowed. This is not allowed. So this commutator has to be only a conserved charge, another conserved charge which transforms like half 0. Half 0 is Q itself. So this tells me that this commutator has to be proportional to half 0, and mu nu q bar alpha j has to be only 0 half by the same argument. So let me try to write mu nu q alpha I as C mu nu alpha beta of q beta j, and C mu m mu nu q bar alpha dot I to be C mu alpha some bar beta dot q beta dot I. What C mu? Mu's are some quantities, objects which I must determine what they are. Use Jacobi identity again and work out what these C mu nu are. Jacobi identity, and if you use that, now what is half? C mu nu alpha beta turns out to be sigma mu nu alpha beta half. This turns out to be this, and that is, let me write now, m mu nu commutator with q alpha I is half sigma mu nu alpha beta q beta I m mu nu. I think it's the other way around. The algebra I have written, the correct answer is this way: q alpha I m mu nu and q bar alpha r dot I m mu nu is, so maybe this is the way I have written there is minus that, and this turns out to be half remember, this object is self-dual and this object is self-anti-dual. So the commutator of q alpha I with m mu nu is half sigma mu nu alpha beta q beta I, and q bar is sigma bar. But that's not surprising, because this is how we give the how spin half fermions are supposed to transform under Lorentz transformation. This is precisely the way spin half, and these are spin half objects, spin half 0 transformed under Lorentz transformation by this is the generator of that transformation. And spin 0 half, the right-handed spin half fermion under Lorentz transformation, these are the generators. So that's not really surprising, that's only a check that we have done things right. It's clear? Because this is precisely what tells us that this object is spin half 0. Because spin half 0 under Lorentz transformation transform like this, and this tells us precisely that it's spin 0 half. This is half 0 and this is 0 half, and 0 half objects transform exactly under Lorentz transformation. Right? So let me put all these relations in one place now, so that we'll look at them all together. See, what we discovered is there can be spin half conserved charges, there can be spin half conserved charges q alpha I and q bar alpha dot I for I1 to some n with their algebra as q alpha I q bar alpha dot j is twice delta ij sigma mu alpha alpha dot p mu q alpha I q beta j is, how did we normalize it, 2 root 2 epsilon alpha beta zij, and q alpha dot bar I anti-commutator q beta dot j bar is 2 root 2 epsilon alpha dot beta dot z bar ij, with zij equal to minus zji and z bar ij equal to minus z bar ji. And then in p mu with q alpha I 0, p mu with q bar alpha I equal to 0, and q alpha I with m mu nu commutator as half sigma mu nu alpha beta q beta I, q alpha dot bar with m mu nu commutator half sigma bar mu nu alpha dot beta dot bar I. And then the usual relation between m mu nu and m alpha beta, that I will not write, and p mu, well, lambda rho. So that forms a closed algebra of conserved charges. So you can give it a name. This was in some sense Lorentz plus this group, Poincaré group. This you can call it a super Poincaré group. That's a name. Now one interesting point to note is that we have introduced n spin half spinorial charges. Q alpha I and Q bar alpha I, where I is 1 to n. These are n of them labeled by index I, which has nothing to do with Lorentz group. So it's an internal space label. Not a Lorentz group label. Under Lorentz group, this index is neutral. And these are n complex objects for every alpha. For every alpha, there are n complex objects. What is the largest rotation I can do amongst n complex numbers? So I can rotate Q alpha I by a un rotation. Internal space rotation which acts on this index I. So which means if I take Q alpha I and rotated Q alpha I to prime, I could write this as some unity matrix times q alpha I u, where u dagger u and u dagger is 1. If I think of these as quantum operators, then a transformation by quantum operators on any observable are given by this object. And if I write u now as exponential I ai times theta, where IA is a certain Hermitian generator of these rotations. This is how we define the rotation, and theta alpha A are the parameters of such a rotation. And since it is a n cross n unity matrix, the number of such generators, which means label A, goes from 1 to 2 to n square minus n square u1. Now this object, if I expand this out as expand it out as one unit operator, dagger is minus I ta theta a on q alpha, this one is 1 plus I b theta b. If I expand this up to infinitesimal object, this is 1 minus I a theta a, because this is u dagger here, and u on this side is I, and that is q alpha I plus I times q alpha I commutator I a theta a at I times q times I here and I times q, that makes into a commutator, right. So this is an abstract generator. Now if I want to write this abstract generator as a representation, some matrix representation, then this object would be proportional to that matrix representation, which means this would be equal to q alpha I plus I times some t a I j theta a times q alpha j. That tells me the commutator of q alpha I with the generator of the u1 rotation is some matrix T A I j, call it A up, times q alpha j. And similarly for q bar dot I a minus T A I j q bar alpha dot j. Well, it will be adjoint of that, it will be this way in fact. Q alpha dot J T A J I. So put it J up, put it J I up, bar. Why TAIJs are n cross n matrices which are Hermitian. So in such a theory, in such a theory, where there I have n spinorial charges, in addition to that, I can have a symmetry which is UN symmetry. So that there are, I have n square conserved charges which correspond to rotating these spin half charges amongst themselves by UN rotation. And the algebra of generators of such a charges is to be like this. And there is a name given to this group, this UN group of invariances. It's called R symmetry. You can have a smaller than that if you in your theory, but this is the largest group you can have. For some reason, for some physical reason, you may say that your symmetry is smaller than UN. But this tells you that in such a theory, the largest possible extra symmetry that you have, internal symmetry of this kind, is only UN. Now let's look at n equal to 1. Do this algebra and check this sign. This sign is important. Is that for bars charges. So R symmetry for n equal to 1 is U1 symmetry, which means just simply phase changes. And these T matrices are just one dimensional, they are just some numbers, which means Q alpha times generator R, let me call this I now R because there is only one generator, is simply 1. And Q alpha dot bar R is minus Q bar alpha dot. Which means that this U1 charge R is plus 1 for left-handed spinorial charges and minus 1 for the right-handed ones, which means this charge is chiral. It distinguishes left-handed and right-handed spinorials. R charge or R symmetry is chiral. That's why I want you to check this sign, because So U is a phase and R is the corresponding charge of that generator of that phase rotation. So this object U is I times R times 1 theta. So R charge is chiral. And this tells us is that under a chiral means means it distinguishes left and right, which means it distinguishes parity. Under parity, Q goes to Q bar. And therefore, R goes to minus R. Okay, we have 10-15 minutes more. So now we have, in a sense, understood the structure of the algebra of possible spinorial conserved charges. There is some simple consequence of it, and that will what we'll analyze now. So if there in nature there are spin half conserved charges, then nature must have one simple property, which is what I'm going to discuss today. Let me write down that one important property. The algebra that we had, that Q alpha I anti-commutator Q alpha dot J was equal to 2 delta Ij sigma mu alpha alpha dot times P mu. Let me rewrite this as what I have raised alpha dot here, and you know how to raise alpha dots through epsilons, and I have raised alpha dot here also through the epsilon. Now let me take alpha and alpha dot same and sum it up, and that I will call and divided by half, trace Q alpha I Q bar alpha dot I take I and I same for every I. That means no sum on I, no sum over I. For every I, take the same I, take alpha and alpha dot to be the same, which means if it's 1, this is 1 dot, this is 2 dot, and sum them. So trace is in that sense, trace is in Dirac space, in the spinorial space. in the sense that you are summing alpha. See, in this relation alpha and alpha dot were independent. Here you sum over alpha and alpha dot. But don't sum over I, but keep the same I for both of them and evaluate this, which means I will rewrite again. Alpha is 1 and 2 and no sum over I is q alpha I mod square, because this is complex conjugate of that. And that object, and from this side I have 2 and I is equal to j without summing, so that's just 1. And remember, sigma mu nu are traceless for mu not equal to 0. So the only one that is with non-zero trace is sigma 0, because sigma 0 is an identity. So that gives me P0 times the trace of trace, and that is 2, but then I have divided by half here. I think I should have divided half here also, right? No, this is because this is see, these are 2 terms. So I have a factor of 2 here. So when I go over to here, that extra factor of 2 I kill here. This is exactly, so this is this object. It's clear what one has done? But for every I, this is true. For every I, trace of this object, which is mod square here, sum over alpha, is twice P naught. Now, if vacuum state, we give it a name, 0 ket, vacuum state, is invariant under supersymmetry, which means these supercharges that we have constructed here, they must kill the vacuum state. These supercharges acting on the vacuum state are 0. Then this relation tells me twice the expectation value of operator P naught with respect to the vacuum state is 0, because Q acting on vacuum is 0. So what it tells me is that vacuum energy in a supersymmetric theory is always 0. Because P naught is energy, right? This is the energy, vacuum energy. So which means if I plot energy, then in a supersymmetric theory, the minimum of this energy is at 0. And then you could have other states. All other states would be positive energy. energy spectrum of a SUSY theory is zero as the ground state, and everybody else is positive. So that's one. Two, on the other hand, if vacuum state is not invariant under if I think of a theory, what it so happens that Q acting on the vacuum is not zero, we have a name for such symmetries. Earlier we have given already a name for such things. Symmetries which are symmetries of the Hamiltonian but not of the ground state, we call them spontaneously broken symmetries. So this would be a case of a spontaneously broken SUSY. But in this case, because this object, because it is squared, is always positive, but its minimum is not at zero. Or P0. Therefore, E vacuum is not zero, and all other states have energies, including the vacuum state, have energies which are greater than zero. So if you want to draw it pictorially, that is vacuum state. Now you remember we did in your exam also, you did you had a field theory with a very special potential, and you discovered, perhaps you noticed, that the vacuum value of that potential was zero. Did you? And then we said that if the vacuum value is zero, in order to get BPS monopoles, we wanted that the vacuum value should, the potential should stay zero, even quantum mechanically, right? And then we said in supersymmetric theories that's what happens. And we some argued when it can happen is the radiative correction, at least one loop have to cancel between bosons and fermions, and that we did that kind of an argument. But this argument tells us exactly that if there is supersymmetry and you started with a potential which was with ground state zero, if supersymmetry is not broken, the ground state can never be, won't have an energy other than zero. Right. So in that theory, under perturbation, under whatever I do, the vacuum state has always zero energy, and the potential has a minimum always at zero. That's because that theory has this invariance. Yes?
Sir, that, as you know, is not a Lorentz invariant. So somehow, so which frame is this 2p0 in? We have not specified any frame to start with till now, but we have suddenly obtained some object which is not Lorentz invariant. So I don't see how we
E is not a Lorentz invariant object. E and P make a Lorentz vector. But what we're saying only about E, that in E will be always 0. And if P is also 0, then E becomes potential, or E becomes mass.
Yes, sir, but from the second line to the third line,
Yes.
That operation we have done, I don't see how it suddenly gave us an object which is not Lorentz invariant.
That's because this object here, when you do the tracing, is a component of Lorentz vector, and the component, this is the 0, 0 component, 0 component. And see, the trace of sigma I is 0. That's why you get only P0 here. This is a Lorentz covariant equation. In this way, you are picking up only one component of this equation, and these are the properties of that component, and that component is energy.
And if I say now go to a new frame, so you're saying that the P0 in the new frame
Will also stay the same, have the same property.
for the vacuum in that frame.
Yes. Because what will that do? That will rotate sigma, these P's. It will become P prime, and this will become sigma prime, because I mean, in order to rotate them. But then if you take the trace again, the same property will hold.
Could it also be that the Q alpha I acting on the vacuum state is 0 in one frame, but in another frame?
No, there is no frame specificity here. Q alpha is any frame is on vacuum is 0. This is
So this is a frame specific state.
under Lorentz transformation. Q changes sigma mu nu times Q. That is still 0 on vacuum, because Q is vacuum.
No, but the vacuum state it itself is a frame specific, right?
No, vacuum state is a frame independent state,
So I was wondering about both sides.
because otherwise a vacuum will break Lorentz invariance. We are not breaking, vacuum doesn't break Lorentz invariance spontaneously.
No, sir. I was thinking more in terms of what happens if you go to a frame which is say I have some accelerating. In that case, it is likely that if Q acting on the vacuum of some frame to start with is equal to 0, then in the new frame it is not, because it is not linked by a Lorentz boost.
See, under Lorentz transformation, we wrote somewhere there, how does Q transform? Sorry, how did we write it? is m mu nu q, right? That's what it is, right? Times theta mu nu are transformation parameters, q alpha. That goes like sigma mu nu q alpha, alpha beta, beta theta mu nu. This is how that under laws of transformation it changes. Now put it on the vacuum. This is 0 because q beta on vacuum is 0. Right? But boosts are part of this. Okay. Anyway, now next class is Wednesday. We won't have Wednesday class because there's a meeting on Wednesday, right?